That used to be me in my heyday. Anyways, today we're going to finish up standard addition, and then we're going to get into our final analytical technique of the semester, chromatography. Let's quickly get back to where we left off with this whole standard addition concept. First, I'm going to remind you of the experiment that we were discussing previously, then I'll remind you about why we would even use this technique in the first place, and then finally, what do we do with all of this data here? So here was the experiment. We have some 10.0 milliliter unknown sample of copper 2+ represented here. Okay, 10.0 milliliters. Unknown in this case means we know that the sample has copper 2+ in it, but we don't know its concentration and we want to quantify that. We might also not know what other chemicals are in this solution. Maybe it's a rather complicated sample that we're studying. Okay, so in this experiment we measure it with AES and it exhibited an intensity of 0.110. So the intensity of the unknown is 0.110. Then 2.0 milliliters additions of this standard known concentration of 2.50 micromolar copper nitrate were added sequentially. In other words, we started with just the unknown, and then we added 2 milliliters of standard, 2 more milliliters of standard, and then 2 more milliliters of standard. And all the while, we're measuring the intensity after each addition, and the signal gets stronger and stronger, which makes sense because we're adding more and more copper to the mixture. Now, why would we add the copper standard directly to the unknown? Well, it's to remove most interference problems, which we spent quite a bit of time discussing in prior lecture videos. By putting the standard directly into the unknown, we ensure that both the known comparison point and the unknown that we're studying are exposed to the exact same chemicals, and thus they're exposed to the same interferences to the same degrees. And so we won't have all of these discrepancies and problems that we encountered when we were talking about the calibration curve with interferences occurring. However, having everything mixed together definitely makes the analysis more convoluted and less intuitive. So let's talk about how we do that analysis. Starting with, why are we doing multiple additions in the first place? Before, we actually learned how to do it where we just measure the unknown and then measure the unknown with some standard added and do a 1-point comparison between the two and solve. But the issue with that is we should never just trust one data point. It's more reliable to add different volumes of standards total and get different measurements of the readings and then ultimately construct a graph, some type of a curve that's going to be more reliable for our analysis. So on that note, what do we do with all of this data to construct said graph? Well, we make note that as we're going through these different additions, we keep on increasing the total volume of the standard that's present, which in turn increases the final volume of the mixture. And then once again, we keep measuring the intensity, that's going up. And then by combining all of these values appropriately, we can come up with the two values that are going to go on our graph. What we do is for each data point, we take the initial concentration of standard before any mixing occurred, multiply by the volume of standard for that particular data point, and then divide by the initial volume of the unknown. And if we do that for all 4 of these data points, that gives us these 4 values here. And those are the numbers that will go on the x-axis of our graph. For the y value, we use a different combination. We take the intensity of each data point, multiply by the final volume, and then divide by that initial volume of the unknown by itself. And then these become the values that get plotted on the y-axis of our graph. And our graph looks like this. There are the 4 data points that correspond to these numbers here. You can verify that for yourself. And then we plot a linear trend line through the data and take it all the way to the x-axis. And we'll get into why that's important momentarily, but I just want to draw your attention down here. That monstrous equation is the equation for that line that we're looking at. We got a little bit into where this equation comes from last time, so I'm not going to go into that during the recap. But suffice to say, if we plot that y value against the x value, we get this line here, and the slope of that line is equal to the intensity of the unknown when it's measured by itself, divided by the unknown's initial concentration. And the y-intercept of that line should in theory be equal to the unknown's intensity. but there will always be a little bit of error. And the concluding statement that we wrote at the end of the last lecture was, if we make this plot of this value versus that value, the negative of the x-intercept is the concentration of the analyte in the unknown. In other words, the initial concentration of the unknown, which is what we care about. But we didn't get into why this is true, so now I'm going to prove that, and hopefully that'll help make more sense of this analysis. So let me reorganize this information. Now I've consolidated all of the important ingredients. Notice that the graph no longer has the trend line shown or its equation. There's a reason for that. We'll see it momentarily. But first, let's just prove this statement here. Why is the negative of the x-intercept the concentration of the unknown? Well, let's start by addressing what the x-intercept means. At x-intercept, the value of y equals 0. And so I'm going to take this graph equation here, and I'm just going to plug in 0 for the left side, for that y value. And then we're going to solve for what the x value is. In other words, what is the x-intercept? So 0 equals, and then we have our slope still, is the intensity of the unknown divided by the concentration of the unknown by itself. And then I could write that whole x value equation, SI times Vs over Vx, but I'm just going to write x value. And we should just understand, and I'll draw this off to the side, that x value really equals concentration of the standard before it's mixed in with anything times volume of the standard over volume of the unknown. And for the record, the reason I keep calling these y value and x value as opposed to just y and x is because I don't want to confuse this x with the actual unknown x, because they're not the same thing, right? X value refers to this combination of terms. That's what goes onto our graph on the x-axis, not to be confused with the actual unknown concentration of x, which is something different, but ultimately something we can relate to the graph. But anyways, to finish off the equation, we have Ix over Xi times x value plus our y-intercept, which is just Ix, or the intensity of the unknown. So from this point on, I'm just going to try to solve for this value here, the x-intercept's value. And I'm going to just do simple algebra. First, I'm going to bring this whole term to the left side by subtracting it from each side, and then I'm going to solve for this. So let's just write it out so that we can have a complete proof. Step 1, bring that Ix over Xi times x value to the left side of the equation, which means it's now negative, and on the right side, we're left with nothing but Ix. From there, how can we simplify? Well, we have Ix on both sides, so let's cancel those. Cancel Ix. And the last thing to do is multiply both sides by x initial. Multiply both sides by x initial. And what we will have is negative x value left over on the left side. And on the right side, we will have concentration of the unknown before anything is done to it. In other words, what we want to learn about. Let's star this. That's our proof right there. That's our answer. This is telling us that our concentration of the unknown must be equal to the negative of whatever the value of the x-intercept is. This isn't just some rule I'm telling you. It's proven here by definition of the x-intercept and recognizing what all of these symbols are in relationship to this linear graph. We come to this conclusion. It can be a lot to take in, but it's beautiful math, and it's a very nice trick for figuring out our concentration. And again, it's a more reliable method than the calibration curve. It does have a disadvantage, which we'll get to momentarily when I contrast the two curve techniques, but let's keep our focus here a little bit longer and use this knowledge to solve for our concentration of unknown based on this graph here. Two ways to go about this. And before I get into them, I'm going to clear some space. There we go. So method 1, which is the drawing an eyeball method. What if I just gave you the information you currently have? No equation, no actual line drawn, just those data points in the graph. How would you figure out what the x-intercept value is? Well, the best thing you could do is eyeball it. Just try your best to draw your own line through the points, take it all the way to the x-intercept, and estimate what that value right there is. And as long as you're in the ballpark, you do this in a way so that clearly it shows you know what's supposed to happen. You would get full credit for this, and you'll get a chance to practice the drawing technique on the homework. So eyeballing it like that, I would say we are at minus, well, this darker line here represents x value 0, so minus 0.1, minus 0.2, minus 0.3, minus 0.4, and so then it's in between negative 0.4 and negative 0.5. So let's just make that negative 0.45. The x-intercept, which really just means the value of x when y equals 0. The x-intercept we are estimating as being negative 0.45. And by that relationship we already covered and proved, if the x-intercept is negative 0.45, the negative of that negative number is, of course, a positive number, which it better be because concentrations aren't allowed to be negative. 0.45, that's our estimate. What's the unit? Well, it's micromolar. How do I know that? Because back when we covered the experiment itself, the concentration of our standard was micromolar, and we never did anything to those units as we were using it for these values here. It's just too cumbersome to write units every time as we're doing all of this. So just go with the rule. Whatever units went into the math, that's what's coming out. So that's how we can estimate by eye. Now, a much more accurate thing to do would be to take those data points and use Excel to plot your own trend line. Of course, I would not expect you to pull out Excel on an exam, but maybe on an exam I would just give you this, the equation for the line, and you just need to know what to do with that information. And here's what you would do. Plug in 0 for y, and then we're just going to solve for that x value there, which is just simple algebra, and if we do it correctly, we will get x is equal to negative 0.433, which again, we just take the negative of that value to get concentration of the unknown is equal to positive 0.433 micromolar. So pretty close to the actual eyeball estimate of 0.45 I got earlier. So not bad for a 2-second sketch with no ruler. And that's all I expect from you. You don't need to kill yourself on these eyeball problems. It's going to be clear if you know what you're doing or not, as long as you're in the ballpark. So that is the standard addition method using graphical analysis. Now let's just quickly compare and contrast what we've learned in the past, the calibration curve, which utilizes external standards that are completely independent of the unknown we're studying, versus the standard addition where the standards go directly into the unknown that we're studying. So the general procedure was just described. For external standards, we just make them separately, and then we compare their signal to the unknown signal. And we do that by constructing the calibration curve graph from our standards data, and then we plug in the intensity of the unknown and solve for the x value. Whereas in the standard addition method, we measure the unknown by itself, and then we progressively add more and more standard into it, and then keep on measuring the intensity, and then we make this type of graph here, which has very different terms going into the y and x-axis compared to the calibration curve. And what we do with that graph is very different as well compared to the calibration curve. We're not just plugging in the signal of the unknown and solving. We are instead solving for the x-intercept, which is guaranteed to be negative, and then we take the negative of that value to get a positive answer, and that winds up being our concentration of the unknown. The advantage of this method is that now everything experiences the same matrix effects, i.e. interferences, and we already discussed that earlier. Now, what the advantage of the calibration curve is that it's simple, and you can ideally use the same curve for multiple unknown solutions. For example, what if we had 20 different unknowns whose concentration we wanted to know? We could, in theory, just measure each of those unknowns and plug them all into the same calibration curve and just solve for x each time. And Excel could do this very quickly in real life. And so it's very nice and convenient. I, in fact, used the same calibration curve in grad school for about 2.5 years. I would just take data on unknowns and plug it into the same equation for 2.5 years. However, for standard addition, where you have to directly mix the standard into the unknown you're studying, you cannot use the same graph. If you had 20 different unknowns, you're going to have to add standard over and over into all 20 of them, measure every single one of those additions, make a graph for every single unknown. It's a lot more time and resource intensive, to the point that it might not even be a reasonable technique to try to employ. Without going into it, I can say that this method would not have worked for those 2.5 years of research I did. So thankfully the calibration curve was fine. So more reliable, but more complicated and harder to do. So that is a wrap for this concept. Next video we will tackle something brand new.